example of what we're going to be talking about. And if you're listening on Integrity, you have to go and click the link to get the sound. I can't have both microphone sound and classroom sound at the same time on the computer, so if you're on Integrity listening to these, you won't get sound on the animation, but the links are all there, so you can go. So I'll restart this. Oh dear. Not good. All right. I'll try that again.
The speed of information processing partially depends on the number of neurons involved in the task. A complex voluntary behavior, such as identifying and reaching for an apple, involves multiple brain systems, sensory, cognitive, and motor, and many neural connections. The elapsed time between recognizing the object and initiating a behavior is thus relatively long. While complex voluntary behaviors are certainly adaptive, there are situations, such as the rapid withdrawal from dangerous stimuli, that require immediate action. A rapid response is one of the advantages of the reflex arm, which involves only a few neurons. In a simple reflex, the entire signaling sequence detection, processing, and response is handled by the spinal cord, without the need for input from higher brain regions. Indeed, conscious perception occurs after the reflexive withdrawal has already begun. Let's examine the reflex arc in more detail. First, specialized sensory fibers in the skin detect the painful stimulus and relay this information to nerve cells in the spinal cord. The information is carried all the way from the skin to the spinal cord by a single sensory neuron without any intervening synaptic connections. The sensory fibers enter the spinal cord and synapse upon the interneurons within the spinal cord gray matter. These interneurons, in turn, synapse upon the motor neurons that control the skeletal muscles. In this case, the flexor muscles in the front of the arm are instructed to contract, while the extensor muscles in the back of the arm relax. By exciting some motor neurons and inhibiting others, the interneurons serve the important function of controlling muscle pairs to generate movement. In this case, the motor neurons that control the flexor muscles are excited, while the motor neurons that control the extensor muscles are inhibited.
Okay. So did you catch the brief phrase that the reaction happens before the person is aware of the pain, right? So this is very fast spinal reflex. All takes place, you've already pulled your arm away from the hot stove before you are actually cognizant of pain. And that is enacted by a series of very rapid steps where an impulse is transmitted. It is initiated as a physical effect on a sensory neuron, which causes that action, the physical action of the neuron causes a depolarization or action potential to occur, and an electrical impulse is transmitted up that sensory neuron all the way to entering, of course, through the dorsal or ventral route. Which one? It's sensory, so is it dorsal or ventral? Dorsal, yeah, good. Just checking. Okay, so it enters through the dorsal route, and here there's a synapse or connection between two neurons that occurs. So this electrical impulse is changed into a chemically transmitted impulse. Because remember, it's neurotransmitters or chemical transmission that occurs as chemicals diffuse across the synapse. Okay? Once we're inside the interneuron, is it an electrical or chemical transmission at that point? It's electrical across the little space of the interneuron. Where does it become chemical again?
The synapse in the muscle.
Yeah. Well, actually, the synapse between the interneuron and the motor neuron is a chemical one, right? Yeah. And then again, electrical impulses travel down the motor neuron and chemical at the muscle again. So this very rapid sequence of events includes a change in the nature of transmission from electrical to chemical at least 3 times, right, in this very simple circuit. How does that happen rapidly enough so that you can pull your arm away from a thorn or a hot stove before you're even aware that it can happen? Well, it happens because nerve impulse transmission is very, very rapid, just like electrical signaling is very, very rapid. And that's what we're going to be talking about today. An action potential is propagated along the length of an entire axon. It is the fundamental signal that carries information from one place to another in the nervous system. However, there are other types of electrical signals that can be produced by the activation of synaptic contacts by external stimuli, including pressure and touch and pain, chemical stimuli, external electrical stimuli. All of these things can also initiate changes in membrane potential, which can reach the threshold of becoming an action potential, or can simply be contained at the local membrane. So that's sort of the picture of where we're going. Everything together. Unplug this.
When solutes, such as ions, are placed in a solution without physical barriers, they become evenly distributed throughout the solution by a process called diffusion, the random movement of particles toward a state of equilibrium. For the mixture shown here, equilibrium is reached when the concentration of each ion is evenly distributed throughout the solution. Neurons, like all living cells, are surrounded by a plasma membrane that is impermeable to ions. This property allows a neuron to maintain different concentrations of ions between the inside and the outside of the cell by preventing the passive diffusion of ions from regions of high to low concentration. In a typical squid neuron, there is a large difference in the concentration of ions, such as sodium and potassium, between the intracellular and the extracellular environments. In addition, the interior of the cell has a high concentration of protein ions, each with a considerable negative charge. The plasma membrane is composed of a lipid bilayer. The hydrophobic interior of the bilayer prevents the movement of ions across the membrane. The only way that ions can diffuse across the membrane is by passing through specialized channels that permit the movement of particular ions while excluding others. These channels can be in an open or closed state. When the neuron is at rest, most ion channels are closed. However, a few potassium channels are open, and potassium ions are therefore free to diffuse out of the cell into the extracellular environment. Note that channels can be highly selective. The potassium channels do not permit the passage of sodium ions. Since only a few sodium channels are open at rest, very few sodium ions flow into the interior of the neuron. If we consider only the potassium ions, which are relatively free to cross the membrane, we notice that the intracellular concentration remains much higher than the extracellular concentration. This is because the potassium ions are pulled by 2 different and opposing forces. First, a diffusion force acts to pull potassium ions down their concentration gradient toward the exterior of the cell. The movement of potassium ions out of the cell results in a depletion of the internal positive charges, causing the potential to become increasingly negative. An electrical force produced by attraction of the positively charged potassium ions toward the negative cell interior generates an electrical gradient that pulls potassium back into the interior of the cell. The diffusion and electrical forces eventually come into balance, and an electrical potential is achieved at which the electrical gradient is exactly balanced by the diffusion gradient. This potential is the equilibrium potential for potassium. At this electrochemical equilibrium, there is no net movement of potassium ions. On average, for each potassium ion that leaves the cell, another returns. The electrical potential across the membrane can be measured using a pair of electrodes. An oscilloscope is used to continuously display the potential difference between the reference electrode and the recording electrode. When both electrodes are in the bath outside of the cell, no difference in potential is measured between them, and the display registers 0 millivolts. However, when the recording electrode enters the cell, the display records a membrane potential of about -60 millivolts. This value represents the resting membrane potential of the neuron, the difference in electrical potential across the membrane during an inactive period.
So, and that is the case at rest. Neurons are completely closed to sodium, but are what we say leaky. They have some potassium channels that are always open. So potassium can flow through down its concentration gradient and out of the cell, but it also can flow back into the cell because it's a positively charged ion, which is repelled by the positive charge here. So as many as go out are coming in, and we say it's reached its equilibrium. And the charge across the membrane at which there's no net flow, meaning no net change, even though potassium is flowing in and flowing out, as many come in as go out, so we say there's no net change in potassium. That potential, in their case, is -60, or as I've written here, -70 millivolts would be, -70 is characteristic when there are other things going on, like sodium-potassium pumps are also running, but if you were only looking at potassium, -60 would be its equilibrium potential. The charge differential across the membrane at which there's no net movement of potassium ion is its equilibrium potential. So. Okay, and we're back. Another animation coming up here. And there's two of these. I'm going to go right to the one that I think is a little bit more interesting. The other one, if you want to look at it, it's on Blackboard. Right, we're running a little short on time.
Differences in sodium and potassium ions across its membrane to conduct action potentials. A pump, called the sodium-potassium pump, builds up these gradients by exporting sodium from the cell and importing potassium. Although the exact mechanism for shuttling sodium and potassium is not entirely clear, experimental evidence suggests the following model. The cycle begins with the pump open to the inside of the cell. In this conformation, the pump has a relatively high affinity for sodium ions which bind to the pump. When bound by sodium, the pump is a substrate for phosphorylation by the high-energy molecule ATP. The energy requirement in this step is estimated to account for 20 to 40% of the brain's energy consumption. The phosphorylation triggers a conformational change in the pump. In the new conformation, the pump has a relatively low affinity for sodium, which it releases outside the cell. The pump now has a relatively high affinity for potassium, which binds to the pump. Potassium binding triggers the dephosphorylation of the pump. Without the phosphate group, the pump returns to its original conformation. Back in its original conformation, the pump has a relatively low affinity for potassium, which it releases into the cell. For every 3 sodium ions that are taken out of the cell, the pump transports 2 potassium ions into the cell. This net loss of 1 positively charged ion for each round of pumping results in a very small electrical current. For this reason, the sodium-potassium pump is said to be electrogenic.
Okay, so electrogenic meaning it actually generates part of the electrical charge across the membrane because of what it does. It's my understanding that we don't actually have a complete conceptualization at this time of exactly how the pump is changing its conformation. But what we do know is a lot, and that the transport of sodium and potassium are definitely interrelated. This was first discovered, and the Nobel Prize was awarded for it in the 1950s by using radioactively labeled ions, both sodium and potassium ions, and noting that they
surrounded by a plasma membrane composed of a lipid bilayer. The hydrophobic core of the lipid bilayer prevents movement of ions across the membrane. This property allows a cell to maintain different concentrations of ions on either side of the membrane. The only way ions can diffuse across a lipid bilayer is by passing through specialized channels. These channels are transmembrane pores that permit the movement of particular ions while excluding others. Channels can be in an open or closed state. Consider a simple system in which an artificial membrane separates two compartments containing a 1 millimolar potassium chloride solution. If the membrane is permeable only to potassium ions, depicted as orange spheres, and the concentration of potassium on each side of this membrane is equal, then no electrical potential will be measured across the membrane. However, if the concentration of potassium is not the same on the two sides, then an electrical potential will be generated. This potential is generated because potassium ions flow down their concentration gradient from compartment 1 to compartment 2 and take their electrical charge, one positive charge per ion, with them as they go. Because the potential gradient across the membrane tends to repel the charged potassium ions, it tends to impede further flow of potassium ions. Thus, as compartment 2 becomes positive relative to compartment 1, the increasing positivity makes compartment 2 less attractive to the positively charged potassium ions. When the two forces are in balance, there will be no net movement or flux of potassium across the membrane. Thus, for a given permeate ion, there is a voltage at which a diffusional force, produced by the difference in internal and external concentrations, will be exactly balanced by an electrical force in the opposite direction. At this point, there is no net driving force, and hence, no net movement of the ion. The voltage across the cell membrane represents the equilibrium potential, E ion, for the permeate ion. The Nernst equation brings together descriptions of the equal and opposite electrical and chemical forces that act on the permeate ion. It allows us to calculate the equilibrium potential from the internal and external concentrations of any ionic species. We can simplify the equation by entering the values for the constants. Note that the units for the Nernst equation are joules per coulomb, which is the same as for volts. Because it's easier to perform calculations using base 10 logarithms and to perform experiments at room temperature, this relationship is usually simplified to where log indicates the base 10 logarithm of the concentration ratio. When the cell is at rest, the most permeate ion is potassium. If potassium is the only ion moving across the cell membrane, the resting potential should be identical to the equilibrium potential for potassium, Ek. We can now apply the Nernst equation to determine Ek for a squid giant axon. According to the Nernst equation, the equilibrium potential for potassium is minus 76 millivolts. However, when we record the resting membrane potential of a real squid axon, we obtain a value of around minus 65 millivolts. Why is there a discrepancy? Is the resting potential really driven by potassium ions? If the resting membrane potential of a cell is driven by potassium ions, then we should be able to change the membrane potential by altering the concentration of potassium in the solution bathing the cell. This is because changing the external potassium concentration alters the concentration gradient for potassium across the cell membrane. When we record the membrane potential while changing the external potassium concentration, we obtain the result shown on the graph. Note that as the potassium concentration in the bath rises, the membrane potential also becomes more positive. In quantitative terms, the results show that potassium ions indeed regulate the membrane potential. As the external potassium...
So just a note there, potassium ions are toxic to neurons if administered in high doses. In fact, one of the old forms of euthanasia was administration of KCl, potassium chloride, which simply totally imbalanced the resting membrane potential of central nervous system neurons and basically killed the animal because it could no longer transmit any impulses, being unable to maintain that potential. As soon as you dump large amounts of potassium outside the cell, it flows into the cell and, as you can see, completely depolarizes the membrane. I'm going to stop there because we're kind of getting close to out of time, and I want to make sure I give you your pure mem, but please go and look at just the last few minutes of this animation to get a better understanding of the Goldman equation, which we kind of breezed over very quickly today. And I'll give you your pure mem at this point, so close up your books.
I'd like to know that whether the channel is just highly sensitive, selective, or exclusive. I don't know.
It's exclusive. It's exclusive, yeah. It is. So it won't let any positively charged ion through. It lets only specific positively charged ions through, yes.
And I don't know that. I can't fully understand why the...
I'll go back to it, sorry.
Why that's the...
There we go. You want that pure mem page? Yeah.
Yeah, why the differential...
This one?
Yeah, is polarizing. I can't fully...
Well, because, okay, so if a membrane allows, for example, a membrane allows a positive ion like potassium to go through, but not a negatively charged ion like chloride to go through, then that would tend to polarize the membrane because potassium would flow down its concentration gradient, but chloride wouldn't. So you wouldn't get as much positive charge through as you do negative charge through, so it would tend to polarize or change the charge across the membrane. Does that make sense?
This...
Why differential permeability is a polarizing...
permeability is have certain direction?
Yeah. Like, so for example, if, let's kind of draw it out. Let's just say we've got high potassium on one side and high chloride, right?
Yes.
Positive charge, negative charge. And the membrane is closed to both, so neither one can move. If you open this membrane only to potassium but not chloride, then because potassium is at low concentration, and let's say so is chloride out here, it's going to go down its concentration gradient. But if this is the inside of the cell and that's the outside, for example, there's also a positive charge that's going to repel it and make it want to come back. And there's this, because chloride is not moving, it's going to want to come back in to be with chloride because chloride is negatively charged. So if the membrane is selectively permeable only to potassium but not chloride, that will contribute to a difference in charge where this side will become more positive with respect to this side because the positive ion can go through and the negative ion can't.
But can this go back?
It can go back. Like, so if this is open, it can go either way.
Yeah.
It can go either way.
So why it just...
Because there's two forces acting on it. There's the concentration force and the electrical force.
Yes.
So in this case, the electrical force makes it want to stay because it's being pulled by negative chloride. But the concentration force makes it want to go. because it's higher on the inside and lower on the outside. So the balance between those two forces is going to create a situation where there's a little bit of chloride or potassium over here, but all the chloride's over here. So if the membrane was initially plus, minus, and you open it then just to potassium, you might get one potassium that goes through. So now you've got a membrane that's plus over here. So so these two cancel each other out, right? And instead, it's actually got a positive charge on one side.
But if the channel is open, but the concentration, potential, and the electric force are balanced, so there's no channel. This is also K-balanced. So I think the concentrate potential will not change.
Well, it's going to change somewhat because there's going to be a balance between the two forces. You've got to balance the concentration force against the electrical force. They're not exactly even. So in this case, there might be some movement of potassium over here, causing a difference in charge across the membrane. That's why we say it contributes to polarity. If you only allow some ions and not others to go through, that selective permeability contributes to the polarity because it selects what can go through and what can't. And those forces are balanced with the electrical forces. You're right, but it does create that. It helps create that difference in charge.
Yeah.
I hope that makes sense.
Yeah.
Okay.
Bring this a while before we cut.